Hello, my name is Taishi Nishizawa, and today I'll be doing a presentation on the paper called Contrastive Estimation Reveals Topic Posterior Information to Linear Models, written by Christopher Tosh, Akshay Krishnamurthy, and Daniel Su. So the outline of the video presentation I'll be giving today is as follows. First, I'll do some introduction on the contrastive learning approach, and then the contrastive learning procedure actually used by the authors. And then we'll look at how topic structure is recovered from the embeddings learned by contrastive learning. And then we'll look at the error analysis, experiments, and the conclusions. So what is contrastive learning? Contrastive learning is a self-supervised learning approach that focuses on learning useful representations by distinguishing between similar and dissimilar pairs. The main idea here is to bring together the representation of similar samples while pushing apart the representation of dissimilar samples. For example, in this scenario we have a data set of animals, and after doing some data augmentations of each sample, we have positive pairs of the same animal. So one positive pair we have here is these two augmented images of a kitten, or these two augmented images of a dog. And we also have a negative pair of this image of a dog and a kitten. And so contrastive learning is really helpful for helping models learn without the need for labeled data, making it powerful for extracting meaningful features from large unlabeled datasets. Next, we'll look at the contrastive learning procedure used by the authors. Next, we'll look at the actual contrastive learning approach used by the paper. So the paper looks at text documents and the similarity/dissimilarity of two texts. So the author's assumption is that allowing the model to learn the similarity or dissimilarity of documents through contrastive learning will lead to useful representations of. And so first, we're given a corpus of documents. Next, we sample two documents, x1 and x2, uniformly from these documents. So with the two documents x1 and x2, we further split them into halves. And with probability of 0.5, we output the halves from the same document, so the top and the bottom from document x1 or from document x2, and this will be our similar pair. And with probability of 0.5, we choose halves from different documents. So for example, the top half of document x1 and the bottom half of x2, and this will be a dissimilar pair with the label 0. And so the objective becomes finding a function that minimizes the difference between the predicted similarity/dissimilarity of the inputs minus the actual ground truth. So here you can see the actual algorithm being used. So as you can see, with probability half, a positive example is created, and with probability half, a negative pair, a dissimilar pair, is created. And the function we're trying to find minimizes the overall difference. Now, next we select landmark documents L1 to Lm and create a document embedding of the following form, where the above represents the similarity of document X to landmark document L1, Li, and the bottom shows the dissimilarity of the two documents. And so here's how that looks like. So we have a set of size M of the landmark documents, and we want to create a latent representation of any document X. And the way we do that is we compare the document X to each landmark document. And so for example, for landmark document Li, we first compute the similarity of document X to Li, and then we also compute the dissimilarity. We take that ratio, and we do this for M landmark documents, and we're left with an embedding vector for that document X. And so if we let f star denote the Bayes optimal predictor of the contrastive learning objective, by Bayes' theorem, we have that if we let g star equal f star over 1 minus f star that we saw before, we get this following expression. So g star of x and x prime equals the probability that x1 is of document x, x2 is of document x prime, over the probability that those two things are happening independently. And if we let L1 and LM denote the M fixed documents that we call the landmark documents, we arrive at an oracle representation of a document X. Next, we'll talk about how the posterior topic structure can be recovered from these embeddings. So in this section, the authors demonstrate that the document embeddings we looked at through contrastive learning can actually capture the underlying topic structure of the documents. Specifically, they show that the linear function of these embeddings can represent any polynomial function of the topic posterior vector, and this enables the recovery of topic information from the learned embeddings. So as you can see in this visual, first we'll do some contrastive learning on a set of unlabeled textual documents, and then we'll arrive at a embedding of a document X compared to landmark documents. And the claim here is that there is a linear transformation of this function that recovers the topic probability distribution W of a given document. So here we'll show how generative topic model processing might look like. So first we'll draw a topic vector W from the set of all possible probability distributions on K topics. And then for document X of length 1 to length X, we'll draw Zi, which represents which category a word belongs to. And then we'll draw the actual word Xi. So for an example, suppose we have three topics: sports, technology, and government. Then W is a sampled probability vector, where we have that with probability 20% we'll have sports, and so on. And as you can see, X corresponds to the actual category assigned in Z. And the claim is that when documents are generated according to this model, the embedding that we get described before of X is closely related to the topic vector W. So first, the paper looks at the single topic setting. So we assume that a document X's probability vector W that we saw before is supported on a single topic. So in other words, that just means W is one-hot encoded for a specific topic of the document. Then we have the following lemma. So for any two documents X and X prime, the G star of those two can be expressed as the following, where eta of X is the topic posterior distribution, and the psi of X is the likelihood that the document happens given the specific topic. So here's the actual outline of the proof for this lemma. The key here is that conditioned on the topic vector W, X1 and X2 are independent from each other. This is because, as we saw in the document generation step, after the topic distribution is sampled, each word in the document X is generated independently, conditioned on W. The second line in this proof just decomposes the joint probability by summing over all possible topics EK. And then the third line is using the Bayes theorem, which we can see from on the right-hand side. So from this lemma, we can conclude that G star, which is our embedding of the text, contains direct information about the posterior topic distribution eta. Now, if we take the psi in the numerator and the denominator portion as the L, we can actually show that this embedding is a product of this L and the posterior topic distribution. And if we just take the pseudo-inverse matrix of the L, we can actually show that this can be used as a linear transformation on the embedding to actually recover the posterior topic distribution. So the authors make two observations here. The first point is that this argument can actually generalize beyond the single topic setting. And the second is that the only use of the structure of documents X1 and X2 that we have used so far is that they are independently sampled, conditioned on the topic vector W. So next we move on to this general setting where there's more than one topic for every document. And so first we consider a set of all vectors alpha of length k that can sum up to m. So here alpha can represent one possible assignment of the number of words for every topic. So for example, alpha I could represent the number of words that are assigned to that topic I. And then we can take the union of all sets S for depending on the size of the document. And next, the pi vector can be constructed as a dot product of all the entries of the topic vector W raised to the power of alpha, which is the number of words that topic has been assigned. So here you'll see that the pi vector is actually of length the size of this union set. And then for every entry, it shows the likelihood that we have that specific word topic assignment strategy alpha I. So next, this set here is the set of all assignments of m words to k topics such that it follows the assignment pattern alpha. Here, Z is a vector representing one possible word to topic assignment that could occur for a document that is of size m. So as you can see, the ith entry of this vector Z can represent the specific topic category for the ith word of the document. Then we have this psi of x, which represents the total likelihood for a document x of length m to follow the topic assignment pattern alpha. Here, the cumulative polynomial vector psi on the right-hand side is a concatenation of all the vectors that we see on the left-hand side. Given these definitions, the paper gives us this lemma that's pretty analogous to the lemma 1 we saw in the single topic case. Thus, the proof of this lemma also follows that of the first lemma we saw, where we're getting the marginal distribution over the topics and then using the key insight that the probability of a document given a certain topic can be factorized as a product of the pi vector and the psi vector we saw earlier. And what we see from this lemma is that we can again say that there exists a direct relation of the posterior, eta, with the document landmark embedding. So in this next theorem, the formula shows that given a set of landmarks, which are anchor documents, we can actually recover the topic posterior information for any document by constructing a linear representation using the landmarks. So the proof of this theorem shows that by using anchor words, which are words that are unique to each topic, we can construct landmark documents, and these landmark documents form a matrix L, which can be diagonalized and inverted. This allows us to linearly express any continuous function, which we see as the pi here, and this function is of the topic vector. Essentially, the proof demonstrates that the learned embeddings retain enough information to effectively approximate any function of the topic distribution with a simple linear operation. Here we say that there exists an X where we can find a vector theta that linearly combines the document embedding of X on the landmark documents to approximate the polynomial function of the topic distribution. Next, we move on to error analysis. So due to approximation error, the actual empirical solution that we find could differ so much from the ground truth function that the ideal oracle representation of a document that we've been talking about could actually not be the one we find. So in this section, the authors show that following some conditions, the fears for this are actually unfounded, and the risk of the approximate solution from the global solution can actually be bounded. So as you can see in this formula here, this shows the actual risk of the approximated solution against the actual ground truth solution. So the authors give a set of 3 assumptions. The first assumption This assumption ensures that as we increase the number of the documents, the unlabeled documents, the error between the learned function f hat here and the optimal function f star will decrease with a probability of 1 minus delta. So this is basically guaranteeing us consistency, and the more data we have, the more accurate our learned function will be. And this follows the idea of pack learnability and empirical risk minimization that we saw in our machine learning class. And the second assumption guarantees that for a sufficiently large sample size, the matrix L, which is used to compute embeddings, is well conditioned. And this basically ensures that the learned representation will capture the structure of the data properly and that the embeddings can be inverted. This follows from the fact that that large singular values of a matrix indicate that that matrix retains most of the information along certain directions. And the last assumption here bounds the outputs of the function. So this keeps the learning stable and prevents extreme values that could destabilize the model. So assumption 3 helps with stability and boundedness in the learning process, and specifically ensures that the prediction of both the learned function and the actual ground truth optimal function remain within the certain range between 0 and f max. And so using the 3 assumptions before, we can actually arrive at this theorem, which provides an upper bound on the risk of the approximation. Here, as you can see, the theta of the L2 norm of this theta shows the complexity of the model, and in the denominator we saw the stability of the function that we saw in the assumptions. And on the right hand side, the epsilon provides an error bound, and as n, which is the number of unlabeled data set, increases, we also see that the epsilon goes lower. And then as m, which is the number of landmark documents, increases, we also see that the risk decreases. Next, having shown that there exists a practical bound on the risk of approximation, the authors move on to empirical experiments that they did on their contrastive learning approach. So before moving on to the actual experiments, the authors address one key limitation of the previous approach, and that has to deal with the number of landmark documents required, as they can be quite large. So instead, what the authors chose to do was to train embedding models instead of the form F1, F2 by minimizing the following. Here we see that the product F1 and F2 is the log of the fraction where in the numerator we have the similarity, and in the bottom we have the probability that they're dissimilar. And as you can see from the G star, the original text embedding, the original text embedding is actually an exponential function of this product. And so by using Taylor expansion of the exponential function up to the second order, we expect the approximate minimizer f hat 1 to be as good of a representation over a document as the version G star, which requires landmarks. And so by doing this, the authors were able to work around the requirement of large size of landmarks by using a different function. So in the first of 2 experiments that they did, they used a dataset called AG News Topic Classification Dataset. And so in this dataset, articles either belonged in business, world, sports, or sci-tech. And so the authors first used a training dataset size of 116,000 unlabeled entries to train the model to learn latent representation of the documents. And then they used 4,000 labeled datasets to fit a linear classifier using logistic regression. and they used a separate testing dataset for the figures we see below. And for the latent representation of the model, the authors used a neural architecture of various depths, and they also used ReLU nonlinear activations, dropout, and batch normalization. So on the left-hand side of the panels, we actually see that their model NCE outperforms with pretty dramatic improvements other than word-to-vec. And notably, the model does really well even with a limited size of supervised training examples. In the middle panel, in the top, we see that the more layers that NCE has, the better the test accuracy is. And then we also see that contrastive loss directly goes down as the test accuracy goes up. This suggests that contrastive loss is a good surrogate metric for downstream performance. Finally, the embeddings using TSNE show that comparatively, their model NCE, their embeddings appear to be better separately compared to the word-to-vec embeddings. So in the next experiment, the authors used the same constructive model form as the previous experiment, but they instead used synthetically created datasets instead of real-life datasets. Here the documents are generated using a symmetric Dirichlet distribution, and so the creation of the document follows pretty similar to the approach we talked about before. And through this experiment, the authors focused on how the contrastive learning model performs in recovering the true topics, and how this depends on factors like the model size, the amount of training data we have, and how similar the document topics are. And so for their Oracle representation, they constructed embeddings of a new document by using 1,000 landmark documents. And these 1,000 landmark documents were also sampled from the same generative process. Then they used the true likelihood matrix L of the landmark documents that we saw before to recover the topic posterior. Now looking at the results, we see that the algorithm is able to accurately predict the latent topics with a pretty high accuracy, especially when the topics are not similar. However, as the similarity of the topics increase, the models suffer in performance, especially with a smaller model size. They also saw that a more frequent resampling of the contrastive learning positive and negative pairs led to better performance. So moving on to the conclusions of the paper. The authors of this paper showed that a document-level contrastive learning approach is able to yield a useful representation for our linear predictor. They proved that there is an explicit posterior topic information ingrained in the embedding expression, and that this guarantees, under some assumptions, that a linear predictor can make use of this embedding for various downstream tasks. And in the semi-supervised learning setting, the authors also showed empirically that there was improvement against baselines like word-to-vec and also bag of words. And this was especially the case in label-scarce environments. But perhaps most importantly, this paper showed proof of the usefulness of learned embeddings of contrastive learning, and this extends beyond text, but also to other modalities that contrastive learning is used, such as images.